Hi everybody. So hopefully you had a chance to look at my first Talos video, which covered basic operation of the instrument. So this video is going to be focused on using the instrument to perform STEM imaging. So this image that you are seeing right here is actually an image that I took while I was recording this demonstration. And this is an image of a single crystal of silicon as viewed along a 110 zone axis. This is a HADF STEM image, and we are obtaining resolution of approximately 1.4 angstroms, which is capable with the Talos F200i. So I am going to take you through step by step how to perform STEM operation with this instrument and how to hopefully obtain images like this. So just a few things to cover first. If you haven't watched the video on general operation of the Talos, please go and watch that one first. Additionally, just like the general operation video, I don't cover things like loading specimens into holders or loading holders into the column because, again, for the Talos, it's identical to what is performed with a TECNI, and I have other videos that cover that elsewhere, and I didn't want to be redundant. And the last thing I want to discuss is that while this video is about operation of the instrument, it cannot be overstated the importance of specimen preparation and specimen cleanliness when you are attempting to perform high-resolution STEM and specifically atomic resolution STEM imaging. So this specimen is a single crystal of silicon that has a minimal damage layer on it and is very thin. I believe the region where I was imaging was maybe 20 or 25 nanometers. There's probably some thinner spots on here that I didn't particularly spend a lot of time to look around, but specimen preparation, right, is, as always with anything related to TEM, very important. And then the other part of that, which is really related to specimen preparation, is having a clean specimen. So if you're imaging and you're building up a lot of hydrocarbon contamination, it's going to be very, very difficult to obtain a high-quality STEM image. Probably more so specifically when you're doing STEM than when you're doing conventional high-resolution imaging. Specimen cleanliness becomes paramount. So if it is permissible for the specimen, you should always perform some type of plasma cleaning prior to insertion into the column. I do have a video demonstrating how to use a plasma cleaner, which I can link in the description below, but I'm not going to specifically show that in this video. Of course, I didn't mention it in the basic operation video, but just like with the TECNI, this instrument does have a cold trap, which is used to provide a surface for contaminants to stick on instead of going onto the specimen. So rest assured, I did have that topped off and nice and cold before I started. And it may still be the case that even with a properly operating cold trap and a plasma clean specimen, you may still get some contamination. I do have another video about addressing contamination that provides some additional tips and tricks, namely performing what's called a beam shower if you're still having issues with specimen contamination. And I will put a link to that video in the description. I did not have to perform any type of beam shower when I did this video, though. I just had to do a plasma clean, and that worked perfectly fine. And lastly, the last thing to mention when you're doing atomic resolution STEM imaging is that specimen stability is critical because the nature of the STEM imaging process is serial rather than parallel. So to acquire a high quality STEM image may take anywhere from tens of seconds to more than a minute, whereas for doing a high resolution lattice image that may only be a second or two. So physical stability of the specimen is crucial when doing STEM imaging. And the way to ensure you have a stable specimen more than anything else is simply time. So the longer the specimen is sitting in the holder and loaded into the column, the more stable it will be with time. And I will also show you there are ways to address specimen instability with the imaging. There is a feature with the Talos software called Velox that allows you to correct for drift by using what's called frame integration, which we will go over, which is a very useful feature. But even that in and of itself is not a substitute for a specimen that is just moving like crazy and not sitting still. So I did have this specimen before I started the demo. It was just sitting inside of the column doing nothing for about 30 minutes before I even got started. So please keep that in mind. And without further ado, let's demonstrate how to perform STEM with the Talos. So the Talos can be operated in STEM mode at any voltage you choose, provided you have an alignment file for it. However, you're always going to get the best resolution at the highest possible voltage for the instrument, which of course is 200 kilovolts. So that's what we're going to work with in this demonstration. You can then go and apply the alignment file for instrument operation at 200 kilovolts, and that will have a set of base alignments in it for STEM mode. Now if you select the beam tab in microscope control, you can navigate to the FEI registers control panel, and I have a FEI register specifically for STEM operation at 200 kilovolts that you can select and apply. And just to go over this really quickly, the STEM FEI register is, again, the way I have the microscope configured, a gun alignment that is specifically optimized for STEM imaging, and it will work basically for the whole range of STEM applications, from doing atomic resolution STEM with the highest possible resolution on the microscope down to higher current STEM probes for doing things like EDS or EELS. We don't have EELS on this system, but we do have EDS, and that will be a separate demo. So the difference between the STEM FEI register and the TEM mode FEI register is the gun lens setting. So the gun lens setting is 7 for the STEM setting, and it's 4 for the TEM setting. And without going into the specifics of what that does, it allows you to get smaller probes when you're operating in STEM mode. So there's no reason why you could not use the TEM FEI register to perform STEM. Again, that's just a gun alignment. But if you're trying to get that absolute highest STEM resolution, you need to use a FEI setting with a higher gun lens. And so that's why I have that additional FEI register. And again, we can manipulate the beam current using the numerical value of spot size. So that FEI register will work well for the entire necessary range of application of doing STEM, from just high resolution imaging to doing analytical work. So we'll go ahead and open up the column valves. And of course, the first order of business will be to find an area of interest. So the specimen, as previously stated, is just a plain single crystal piece of silicon that has been wedge polished and I believe lightly ion milled. So this is not a fib lamella. And you can actually see on the left side of the flu cam image there, that's the edge of the specimen. So that's where we're going to focus on imaging, because that's where our specimen is going to be thinnest, obviously. So once we have an area selected, we need to get it to eccentric height. And this is just like what was described in the general operation manual. So I'm in SA mode. My indicated magnification is 11,000x. And I'm going to use the specimen edge there as my reference. As you can see, we're clearly not at minimum contrast. So I press eccentric focus on the right-hand control panel, and then use the Z-axis buttons on the right-hand control panel to minimize the contrast. And now I'm at eccentric height. So the only other thing we need to do really is get the zone axis alignment. Again, if you're working with a single crystal, kind of roughly in the ballpark. We will make another adjustment when we go into STEM mode. So hit diffraction on your right hand control panel. Then you can see the diffraction pattern. And you can see we're not quite on the zone axis where we have the beam positioned. So we'll make an adjustment with the tilt controls on the left hand control panel to get this in the ballpark. And again, this doesn't have to be perfect necessarily, but we could get a little better because we're going to make an adjustment when we go into stem mode. I didn't make a big adjustment to the tilt, so the specimen should still be at eccentric height, but if you notice that it is very much still in contrast, you would need to use the z-axis controls to bring it back to eccentric height. But we don't need to do that because the adjustment to the tilt was fairly small, so there's no adjustment needed to the z-axis to get it back to the correct height. So that's all you need to do before going into stem mode. So now you can just go to the stem tab, and in the stem imaging control panel, just select the stem button and you will enter into stem mode. And then you can select the beam tab and microscope control, then go to the beam settings control panel and set your numerical value of spot size. So you have to make this adjustment to the spot size once you go into stem mode. So the spot size that you have in conventional mode doesn't transfer over when you enter into stem mode. And so again, we of course know that higher numerical value of spot size means smaller beam. So for doing atomic resolution stem on this instrument, 7.6 is kind of the lowest numerical value you can go and still get atomic resolution. You will get the best at 10 or 11. There's really no point in going to 11 in my opinion. You end up losing too much current. You don't really get a benefit as opposed to just using 10. So for doing atomic resolution, to start with anyway, we will use 10. If you wanted to do something like EDS, obviously you could use a lower numerical value spot size, something like 1 or 2 or 3. So then we can return to the stem tab and microscope control, and in the stem detector control panel, you can select insert detectors to retract the stem detector, which automatically inserts when you enter stem mode. In the same control panel, you can adjust the camera length, and we're going to adjust this to a high value for alignment purposes to make it easier for you to see. I normally don't do this at anything less than about 500 or 600 millimeters indicated. So then you can select the Tune tab and microscope control, navigate to the Apertures control panel, and insert the largest condenser aperture. What we need to do now is find an area on the specimen that is mostly amorphous for doing alignment purposes. So if you take your focus knob and you set the focus step fairly high and you defocus the probe, you will actually see an image of the specimen like we see here. So on the left, that's actually the edge that we were seeing in conventional mode, and I know that as I go close to that edge, I'm going to be getting more amorphous material in the specimen. And so once I'm a little bit better positioned over the edge, I can readjust my focus until I see a Ronchigram. You may also need to adjust the display settings on the FluCam to make this easier to see. I also like to remove the circle marks from the FluCam image while doing this. There's a shortcut on the FluCam toolbar. So now you can see we're near a, or at a, mostly amorphous area. So we only have a direct disk, and we see that flickering area in the middle, so we're ready to do the alignment. I do like to manually adjust the exposure time for the FluCam to 50 milliseconds when doing this. And you can do that easily by just selecting that auto checkbox in the settings tab to the right of the FluCam, and then you can set the exposure time to 50 milliseconds. So you can adjust the focus till you see the flickering part like that in the middle of the Ronchigram, which is what you need to start with. So the first step is to make the rings in the Ronchigram circular. So if we go to the Tune tab and microscope control, you can navigate to the Stigmator control panel and select Condenser. When you do this, be sure to select Condenser and use your multifunction knobs to make the rings circular. we will have to make another adjustment to the stigmation in the final image, specifically when we're doing atomic resolution imaging. If you want to shift the Ronchigram on the FluCam image, you can select diffraction alignment from the direct alignments control panel and then use your multifunction knobs to shift the Ronchigram around. Then I just defocused the probe because I was looking for an area that was a little bit more amorphous, and so I found one here, and then I refocused the probe, and we'll move on to the next step. So the next step is the rotation center. Before doing this, I like to set my focus step to 4, so you can use the outer focus knob on the right-hand control panel to set this to 4. I also like to turn off those circular marks on the FluCam before doing this. Again, there's a shortcut on the FluCam toolbar, and then in the direct alignments control panel, you can select rotation center intensity. The focus will automatically start pulsating when you do this, but you can turn it off by simply turning the outer focus knob on the right-hand control panel counterclockwise until the pulsing stops. And now what you're looking for is when you take your focus knob and you expand and contract the Ronchigram, you're looking for that point of expansion and contraction to be concentric with how the Ronchigram expands. So you can see right now when I adjust the focus, it's kind of expanding down and to the right. So now you want to use your multifunction knobs to make an adjustment and then check again with the focus to see if it looks any closer. You want to set your multifunction knobs to the finest setting when you do this, so I just hit that fine button above the left multifunction knob a couple times, and that puts it on the fine setting. You're not really concerned with the position of the Ronchigram inside the condenser aperture while you do this. So please keep that in mind. You're just concerned with how the Ronchigram expands and contracts. So right now that looks pretty good. And then lastly, we will return to the apertures control panel and insert the 70 micron C2 aperture, which is the optimal sized aperture to get us the smallest possible stem probe. And once again, we want to center the C2 aperture around the point of contraction of the Ronchigram. So again, you can just pulse the focus knob to find the center of the Ronchigram, and then you can hit adjust next to the condenser aperture in the apertures control panel to move the aperture around that point of expansion and contraction as needed. And once it's good, just select adjust. And then you can return to the stem tab and microscope control, then go to the stem detector control panel, and then you can adjust the camera length to what will be used for doing the stem imaging, although we may make an adjustment to this later. On this instrument, you need a max indicated camera length of 98 millimeters to form a HADF image, so that's what we will set this to start with. And next we can navigate to Velox and select HADF from the main toolbar, and that will insert the HADF detector and start the live stem image by activating view mode. And you can use the magnification knob on your right-hand control panel to adjust the indicated magnification as needed. You can adjust the dwell time for the live image by using the plus or minus buttons to either double or halve the dwell time respectively. For just searching around, I tend to use a fairly short dwell time, maybe only 4 or 5 microseconds. And now I'm going to use the joystick to center an area of the specimen that I know is a little bit closer to zone axis alignment in the middle of the image. So if I select view from the toolbar in Velox, that will freeze the probe, and then I can click and drag on the little red marker and position the probe anywhere I want. In this case, the beam is blank, so I can just select the unblank icon from the toolbar, and now I'm seeing the seabed pattern on the FluCam from wherever the beam is positioned. So it is a little difficult to see here, but my direct disk and my seabed pattern is not centered inside my stem detector rim. So I can go to my direct alignments control panel, which in this case is in the stem tab, select diffraction alignment, then use my multifunction knobs to center the direct disk inside the detector rim. And now what I'm looking for is, am I on zone axis? And again, this is probably a little difficult to see on the FluCam image, but I'm not, so I'm going to use my alpha and beta tilt controls on my left-hand control pad to tilt so I am on zone axis. Then I will go back to Velox, select View from the main toolbar to start the live image. And I'm going to mag out till I can see the edge of this specimen. You can do an automatic adjustment to the detector settings by selecting the detector settings panel in Velox on the right side and then selecting auto. I will go through how to do this manually as well. So we just did a little bit of tilting, so I want to verify that the image is still in rough focus. So I'm looking at the edge of the specimen here for this. It's probably a little bit difficult to see, but it still looks reasonably well focused. So I'm not going to make an adjustment to the specimen height, but if it wasn't in focus, I would use the Z-axis buttons to focus the image and not the focus knob when doing this. We didn't really tilt that much, so there really shouldn't be a huge need to adjust the height anyway. So now I will increase my indicated magnification to at least a few million X indicated, and then I will pause the live image by selecting View from the main toolbar in Velox, unblanking the beam, and then dragging the beam position marker to the middle of the image. And now I will use the focus knob with a setting of maybe 2 or 3 to dial in the focus to our starting point, and then we'll have to look at the actual imaging when we want to get the best possible focus. So the way I'm doing this is by looking at the Ronchigram, and what you're basically looking for is that blow up condition in the Ronchigram where you see the features in the direct disk basically explode. And I'm going to make an adjustment here to the camera length. I'm going back to microscope control in the stem detector panel. I retracted the detector, and then I'm going to increase my camera length to make this easier to see. So right there, we have a high camera length. You can see there, I'm actually seeing like lattice features. So right about, see, that's too much. And then when we get close right there, you see it's expanding. Right about there is what we want, is something like that. And that's, again, the starting point for the focus. And then we'll set the camera length back to what we were using for imaging, and we will resume the live stem image in Velox. Again, I can just hit HADA from the main toolbar that will reinsert the detector and restart the live image using view mode. So now we will finally dial in the focus, and to do that you want to use a focus step of 1, and you also want to increase the dwell time in view mode. I think this is either 10 or 20 microseconds, and then you can adjust the focus until you get the sharpest image possible. And we're also going to have to make an adjustment to the Stigmation to really dial this in if we want the best possible resolution. But another thing we can do too is we can actually rotate the scanning pattern using the scan rotation feature on the main toolbar in Velox. So we have certain features aligned how we want them. So as we're viewing the silicon here along a 110 zone axis, if we have the features oriented so the dumbbells are running left to right, it's going to make doing the Stigmation a lot easier. So you can adjust the scan rotation using this box on the toolbar here in very fine increments. I think it's 1/10 of a degree until you have the dumbbells running left to right. You can also add in a square annotation here, so you have a nice straight edge as a reference. So you can see here I'm not quite perfectly aligned with those dumbbells going left to right. So once I have this basically perfect, I can delete that square annotation, and then we will maybe perform a little more fine focusing and dial in the stigmation as well. And I basically have the scan rotations set pretty much perfect, so my dumbbells go left to right. And then once you're ready, just click on the annotation and then select delete to remove it. So as I mentioned previously, we can do a manual adjustment to the detector contrast and brightness settings. So if you go to detector settings panel in Velox, you can select scope tool to see the green signal line. Then you can go back to stem detector in microscope control and select MF knobs, and your multifunction knobs will then be activated to adjust the contrast and brightness. And you want that green line basically to fit between that upper dashed and bottom dashed line. And at this point now we can adjust the stigmation. So if you go to the Stigmator control panel, make sure to select condenser, and then you want to set this on the finest setting possible, so hit that minus button above the left multifunction knob a couple times. That will put it on the finest setting. And you can tell if there's astigmatism present because when you adjust the focus back and forth from under to over focus, you will see streaking in the image that basically reorients by about 90 degrees. So once you have that streaking removed, then you know your astigmatism is set correctly, or corrected correctly, I should say. And then when you're ready to acquire your final image, just select Acquire from the toolbar in Velox, and you will start acquiring your stem image using the acquisition settings. So I have this set with a 1024 by 1024 resolution, and I believe the dwell time here is it's either 20 or 40 microseconds. I will show you how to adjust that shortly here. The scanning stops and or the beam blanks after you do an acquire. You can of course just select view from the main toolbar and then unblank the beam using the icon in the toolbar, and then your live image will start again. Of course, just like when using the SATA camera, your acquired images will go to the processing portion of Velox. So one thing you can see in this image is that we see a little distortion left to right because of drift in the specimen. And we will go over one way to deal with that in a moment. Another thing you can do too is you can use the reduced area scan to aid in focusing. Some people like to do this, some people don't. It's kind of a matter of personal preference. But you can use this to help you dial in the focus, or if you want to use it for dialing in the stigmation, that also helps. Again, it's kind of a matter of personal preference. You can kind of see though, there's a little bit of movement left to right. So what I'm going to try doing here is doing an acquire with a little bit shorter dwell time, I think half of the one that I used before, and that's going to reduce our signal to noise ratio, but that should result in an image with less instability. So again, you can just use plus or minus from the main toolbar and then start a new acquire. Then we can go here to the two images, and you can see there's less distortion in that second image. So right now my indicated magnification is 5.1 million x. This and the next setting up works well for atomic resolution imaging. Kind of the lowest end in terms of the magnification where you can do atomic resolution STEM imaging is about 1.8 mx, or you could probably go one setting below this. So we'll do an acquire here just so we can see how this looks. And if I now go to the processing part of Velox, if I click on the image and then scroll in with the mouse wheel, I can digitally zoom in, and we can see we still get atomic resolution detail in that lower mag image. The highest practical indicated magnification for doing atomic resolution STEM, in my opinion, is 7.2 mx indicated. There's really not any benefit to going higher than this. So you can see here we have some really nicely well-defined silicon dumbbells. We can do an acquisition. Again, I'm going to drop the dwell time down here just a little bit. And again, we do have a little instability. The image is kind of dragging a little bit left to right. So this segues us nicely into how to use frame integration to deal with drifting specimens. So if you click that STEM imaging button on the toolbar, if you click on the Series tab, you can input settings for acquiring a series of images at short dwell times. So basically, the way this is set here, I'm going to acquire 30 images with a dwell time of 2 microseconds each. And so each of those images obviously doesn't have a lot of signal, but then I can integrate them and form an image that effectively has more signal. So once you have your series parameters input, you can just select the series acquisition button from the Velox toolbar, and it will start acquiring however many images you told it to, which in this case is 30. And again, each of these images looks really noisy because it only has signal collected over a dwell time of 2 microseconds a pixel. So obviously the individual frames don't look very good, but as we'll see here, we can do an integration and end up with something that looks quite aesthetically pleasing. So once your series acquisition is done, you can go to the processing portion of Velox, and you can select processing from the pull-down menu, DCFI, and make sure you select the option for periodic images. And so you will see an extra panel now that shows the integration up to the number of frames that you had. So if I drag that bar all the way to the left, that's just one frame. You can see what happens as I go to the right. And you can see I have a very nice image. And because each image has a short dwell time, it's not very susceptible to drift. But when I integrate them all together, I have a really nice image. I'm not going to go through it because I covered it in the general operation video, but doing the batch convert of the stem images with Velox is the same as doing it with the SATA camera. It's really nice. The software works in both modes the same. And we're going to do one more drift corrected frame integration here. So I'm just going to select the series option, and I'm going to set my dwell time to 1 microsecond instead, after I did a brief adjustment to the focus, because the focus might have been a little bit off in the last series acquisition I did. So this is going to be a little bit quicker. So I'm going to have a little bit less signal in each image, but again, once we do the frame integration, we should end up with something that's very similar to what I would get if I did a single pass with 30 microseconds a pixel. So when the acquisition is done, if you want to pause the live image and blank the beam so it's not hitting your sample, just be sure to select View from the toolbar and then select the beam blank icon, and then the beam won't be hitting your sample, which is a good general practice. And then we can return to the processing portion of Velox. You can select the series acquisition you just did, and then scroll through each image in the series here if you want. They all look pretty much the same. Then go processing, pull down, select DCFI. Make sure you select the option for periodic images, and then it will do the integration. And so we see once again that by using DCFI, we can overcome the limitations that we would get by using a long acquisition time for a single pass by using a bunch of short acquisition times and then integrating them. So you can see I really don't have any distortion in the DCFI image. One caveat I will say is that if you're going to publish an image like that, you do have to specify that it was a drift corrected image. You can't just leave that bit out, but it's accepted. People do that, so there's no harm in doing it. Just make sure that you're honest about it. Okay, so let's go back to the live image here. I'm going to decrease my dwell time. Then I'm going to mag out till I can see the specimen edge. And then I'm going to position the specimen edge in the center of my image. And then we're going to adjust the numerical value of spot size and collect some stem images again so we can see the difference in doing that. So we have to reperform the alignment if we're going to adjust the numerical value of spot size. So you can select View from the toolbar in Velox to freeze the probe, then go back to Microscope Control, go to the Tune tab, and you can change the spot size. I'm going to adjust it to 7. 7.6 is kind of the limit in terms of the lowest numerical value where you can still get atomic resolution. And we have to reperform the alignment. So I'm going back to the Stem tab in Microscope Control. I'm going to retract the stem detector in the Stem Detector control panel. I'm going to increase my indicated camera length substantially here to make this easier to see. And then I'm going to adjust my focus till I have a defocused Ronchigram and I can see the specimen, and so I know I'm over an area that is mostly amorphous. I will then reinsert my largest C2 aperture, so I'm going to the Tune tab, going to the Apertures panel, and then inserting the 150 micron aperture. And then I see that my Ronchigram features are not quite circular, so I'm still in the Tune tab here. I'm going to make a quick adjustment to my FluCam exposure, drop that down to 50 milliseconds. Go to the Stigmator panel in my Tune tab, use my multifunction knobs to make the features circular. Next thing, of course, is the rotation center. So I'm going to set my focus step to 4, go to Direct Alignments Control Panel and select Rotation Center Intensity, then use my large outer focus knob, turn it all the way counterclockwise until the pulsing stops. Then I can pulse it manually. I'll make a quick adjustment to the FluCam here to make this a little easier to see. Again, I might have to manually adjust my exposure time. And again, what I'm looking for here is, as I adjust the focus and expand and contract the Ronchigram, is it expanding concentrically? So you can see it's kind of expanding down and to the right. So again, I'm going to set my adjustment for my multifunctions on the lowest setting. Just hit that fine button above the left knob a couple times, and then adjust my knobs. Then check with the focus to see how it's expanding. Then adjust the knobs, check with the focus so it's iterative until it's going straight in and out. And that looks pretty good right there. Then you can select Done in the Direct Alignments Control Panel, and then go back to the Apertures Control Panel and reinsert the 70 micron C2 Aperture. And then we have to recenter it, so you can pulse the focus to see where the aperture center is. Might be a little hard to see here. And select Adjust next to the aperture in the Apertures Control Panel. And use your multifunction knobs to center the aperture around the center of the Ronchigram. Then we'll go back to the Stem tab, then to the Stem Detector panel, and then we will reset the indicated camera length to 98 millimeters. We'll then insert the Stem Detector using that same control panel, or we can just select HADF in Velox, and then it will automatically insert and start the live image. You can see the detector is a little saturated, so if you go to Detector Settings in Velox, you can select Auto, and that will do an automatic adjustment to kind of get you in the ballpark. I'm then going to take the stage and move back to where I was before, where I had good zone axis alignment. You can see on the FluCam, it's easier to see my detector rim now because I have more current in my probe. So now we're going to set the focus to kind of the starting ballpark value for our area of interest. So you can select View in Velox to freeze the stem probe. So it's now positioned where that little marker is, the little red marker. Then you can go back to the FluCam, increase your indicated camera length to make this easier to see, and then use your focus knob, set it maybe 2 or 3 to blow up the Ronchigram. So we can see here, right about there. So we're a little bit off, not too much. And then we can set the indicated camera length back to what we were using before. And we can reinsert the stem detector. You can see here I'm basically centered inside the detector rim, but I'm going to make a little adjustment here. So in Direct Alignment, select Fraction Alignment, use your multifunction knobs to center the Ronchigram inside the detector rim. And you can go back to Velox and restart the live image. Focus has been set back to step size 1 again. And you can see we have a lot more signal in the picture now because we're using, obviously, more current in the probe So once you have the focus as good as you can get it, the process of adjusting the stigmators is the same. Again, use the condenser stigmators. You want to look for streaking that reorients by 90 degrees as you go from over to under focus. So we can see we still have some here. Again, make sure you use the finest setting on the multifunction knobs when you're adjusting the condenser stigmators when doing this. Again, you can use the reduced area scan if that helps you. So the stigmation is actually off quite a bit here, believe it or not. And I remember when I did this, I accidentally over adjusted. So you're going to see a little bit of a discontinuity in the video here between now and when I get it closer to where it should be. And once we have this dialed in, we will do some acquisitions again. We'll go through doing the frame integration again to compensate for the drift. So right about here, you're going to see a little discontinuity in the video, okay, where the stigmator adjustment is closer to where it should be, and you're going to see how this should look once I have it dialed in perfectly. Again, you can see clearly I have streaking that goes diagonally here, changes from going over to under focus. One other thing to point out too is that you have to be sure that you are on zone axis, or else you might be seeing the streaking just by virtue of not being properly aligned with the zone axis. So again, you have to eliminate things. If your zone axis alignment is good, your alignment is good otherwise with the stem probe, then your stigmators are off, which is the case here. And I can see it's, well, maybe it's kind of hard for you to see, but my zone axis alignment with the seabed pattern is good. So I just have to adjust these stigmators, and you will see once this is dialed in what it looks like. I'm pretty close right now. So right about here, I'm really, really close. Just going to make a little bit more of an adjustment. We'll set the focus how we want it. Oh, there we go. Perfect. Get the focus good. And that's it right there. And then we'll go ahead and we'll do an acquisition. So you can select acquire from the toolbar in Velox. I didn't do a detector adjustment, but you could do that the same way as I showed you previously. So we'll compare this image at spot size 7 with the one at spot size 10. So we'll go to the processing portion of Velox, and there's the image at spot size 7. And there's the image at spot size 10. So you can clearly see the difference between those two. The spot size 10 has better detail albeit at the expense of poor signal to noise because we have less current. We do still have some instability in the specimen, so let's go ahead and do a drift corrected frame integration image at spot size 7, which we will of course compare to the one we collected at spot size 10. So again, I'm using the same settings I had for the last series acquisition I did at spot size 10, which is 1 microsecond and 30 frames. So we'll go ahead and select View from the toolbar to freeze the image and then blank the beam. Then we'll go to the processing portion of Velox and we'll select the series we just acquired here. We can scroll through, see they're all pretty noisy. Select Processing, DCFI, make sure you select the option for periodic images. And we see we have a nice integrated image here. We can of course compare it to the one taken at spot size 10. Clearly there's more detail, although you can see here the magnification is different. And we want to make sure we have an apples to apples comparison, so I'm going to do another series acquisition at the same magnification I used for the image collected at spot size 10, just to make it easier to see. So again, I'll go ahead and bump up the indicated mag, dial in my focus on the live image, and then collect the series. All right, we'll go ahead and freeze the live image, blank the beam, go back to the processing portion of Velox, do the same thing, select the processing pull down option, then DCFI, and then for periodic images. And then now we can do a clean comparison. So there's spot size 7, and there's spot size 10. So clearly you can see more detail. In fact, if you look at the FFT here, you can see the 004 spots in the spot size 10 image, but you don't see them in the spot size 7 image. So finishing up in STEM mode is fairly straightforward. The first thing you want to do is make sure your STEM probe is not scanning. So just select View from the toolbar in the acquisition portion of Velox. You don't want to blank the beam though. So just freeze the scan. But again, the beam is unblanked. Then you want to neutralize the scan rotation, set it back to 0. There's a little shortcut in the toolbar. And then you just want to select HADF also in the toolbar, and that will take the instrument out of STEM mode and retract the stem detector, and then the instrument will be placed back into conventional mode. And that is how to perform STEM with the Talos F200i. So the only other thing I need to mention is that if you switch from STEM back into TEM mode and you want to do some conventional mode imaging, you will have to perform instrument alignment again in conventional mode. The alignment of the microscope is heavily dependent upon the state that it is in, which is why you'll notice when we went from conventional into STEM mode, the only things we did were set specimen height and do a rough zone axis alignment, because it would have been pointless to do all the other alignments because the alignment was going to be different when we go into STEM mode. So just bear that in mind if you need to do any additional imaging when you're done in STEM mode. So as always, please let me know if you have any questions or comments. I do plan on making 2 more of these demonstration videos for the Talos. One will cover 2-beam imaging, and one will cover performing EDS while also operating in STEM mode, which will get us into things like line scans and maps. So with that, thank you for your time.